everybody, and welcome back to one of our live sessions. I'm Olivia, and today I have the distinct pleasure of being able to host John Preskill for our first Distinguished Speakers Lecture of the summer school, which is really very exciting for me, and I hope for you as well. John, to me, really needs no introduction, but I do have a small bio and intro prepared, so I will read that very quickly, and then we will get started. So, John Preskill is the Richard Feynman Professor of Theoretical Physics at the California Institute of Technology and the founding director of Caltech's Institute for Quantum Information and Matter. After graduating summa cum laude from Princeton and earning his PhD at Harvard under Stephen Weinstein in the 80s, he joined Caltech's faculty in 1983 and has been there ever since. John began his career in particle physics and cosmology, but is now best known for pioneering work in quantum information science, ranging from error correction codes to thought leadership across the board. His freely available lecture notes and blog have made him an influential educator and science communicator. And among these many honors, John Preskill is a member of the U.S. National Academy of Sciences and a fellow of the American Physical Society. He has received multiple Caltech teaching awards for mentoring more than 50 PhD students. All right, so that was a quick little intro. John, I think, just has to share his slides again, but while you do that, John, feel free to just bring them up the way you did before. I just want to remind people that we are going to be taking questions at the very end. So please use the chat Q&A button on the right to post your questions for John, and I will do my best to field those at the
I think we lost Olivia for a second, but she'll be back. Oh, here she is. Oh, Olivia, go ahead. Okay. All right, John, I think you can get started. I think what Olivia was saying is if you want to ask your questions throughout the chat throughout, we will. Oh, I think we might be having some technical difficulties, everyone.
Am I back?
Yes, you're back.
Okay. All right. Oh, and we lost John.
Sorry, everyone.
Just give us a sec, guys. Hey, John, can you hear me now? I don't think John can hear us. John, can you hear me?
Does anybody see or hear me? Maybe you can put something in the chat. So that was a yes. They can hear me. Okay. Because I seem to have disconnected, but think I've reconnected. All right. I am going to attempt to share the slides again. We'll see if it works this time. All right, so somebody say yes, you can see my screen. Because I can't hear anything. Okay, I guess that's a yes, so here we go. Sorry for the delay. All right, well, I'm sure Olivia said wonderful things about me, but I don't know what. Thank you, Olivia. And I'm honored to have this opportunity to talk to you today about Feynman's dream, simulating nature with quantum machines. I'm going to tell you a little about what Feynman had to say in 1981 when he proposed the idea of a quantum computer, and then I'll discuss some of the things that have happened in the 44 years since then. If you'd like to see more details, I wrote an article that's on the archive and was published in a new edition of the Feynman Lectures on Computation on this theme. So this talk is an update 4 years later of that discussion. Let's also remember that just a few weeks ago, we celebrated another anniversary, the 100th anniversary of the discovery of quantum mechanics. The story goes that Werner Heisenberg, who was just 23 years old, trying to seek relief from his hay fever, went to the remote island Helgoland in the North Sea, and while there, had an inspiring insight, a breakthrough that made him the first to articulate a mathematical framework of quantum mechanics. Heisenberg himself told this story in a very romantic fashion in his memoir, which was published in English in 1971. He described doing computations late into the night to verify that the formalism that he had developed was on the right track. And then before sunup, took a hike to a rock overlooking the ocean and watched the sun come up. So I read that when I was a high school student, when that memoir had just come out, and I was duly impressed. Let's also call out another of the early heroes of quantum mechanics, Paul Dirac, who formalized and clarified the quantum mechanics of Heisenberg and Schrödinger. And particularly relevant for today's discussion, as far as I know, Dirac was the first to articulate that with the many electron Schrödinger equation, we have a theory of everything that matters in everyday life. It's the theory that describes many electrons interacting electromagnetically and quantum mechanically with each other and with atomic nuclei, which underlies all of chemistry and material science. But as Dirac pointed out, the exact application of these laws leads to equations much too complicated to be soluble. Dirac was thinking of problems with just a handful of electrons when he said that. Dirac was Richard Feynman's scientific hero, and it may seem odd to us looking back that it took over 50 years for Feynman to suggest that if we want a machine that can solve the many electron Schrödinger equation, it should be a quantum machine, not a conventional computer. Let's remember, though, that for Dirac in the 1920s, computation is something that we do with a pencil and paper, not with a machine. Feynman gave a talk at a conference at MIT on the physics of computation in 1981. A transcript of the talk was published, and it's still interesting to read today and is still frequently cited. He made his goal clear. It was to have a simulation of many particles where the number of computer elements required to simulate a physical system is proportional to the space-time volume of the physical system. And he pointed out that with conventional computation, that doesn't work. Because if I want to keep track of many electrons, the number of quantum amplitudes in the wave function that we need to follow grows exponentially with the number of particles. So we asserted that cannot be simulated with a normal computer. But then he made the leap of suggesting that what we should use instead is a quantum computer. And he suggested that there didn't seem to be any reason why we shouldn't be able to simulate many particles interacting quantum mechanically if we built the computer out of quantum computer elements. And as he emphasized, this is a new model of computation, not a Turing machine, a machine of a different kind than had been considered before. And in his talk, Feynman went at some length into the reasons why we don't expect a conventional computer to be able to simulate such many particle quantum systems, even if that computer is equipped with a random number generator to emulate the randomness of quantum mechanics. He spoke of the hidden variable problem, the idea that it's not possible to keep track on a probabilistic conventional computer of all the entanglement among the particles. And he discussed in some depth and at length the idea of Bell inequalities, which show that quantum correlations are different than the correlations among parts of a classical system. And he discussed some of the experimental evidence that the Bell inequalities are violated, as it was known at that time. There are no references, and he never mentions John Bell. Feynman could get away with that, but you and I probably couldn't. And Feynman brought his talk to a rousing finish when he said, if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. And he was right about that. I think we can say 44 years later that it's still a wonderful problem and it still doesn't look at all easy. Now, to be fair, I should emphasize that there were other people discussing the idea of a quantum computer in the early 1980s. One of them was the mathematician Yuri Manin, and he made the relevant point that if we want to keep track of the state space of a quantum system with many particles, that state space would grow exponentially with the number of particles. And he observed that that points to a much larger potential complexity of the behavior of a quantum system if we compare it to a classical imitator. And Paul Benioff also spoke of mathematical models of quantum computation in 1980. But for Benioff, what was of central interest was not quantum complexity, the problems quantum computers could solve, but just the foundations of computation itself. And he was interested in a quantum world, whether it would be possible to do computation with negligible energy dissipation. That was also a question that interested Feynman very much, and he discussed it at length in a talk that he gave a few years later. Before we leave Feynman, I would also like to recommend that you read another visionary talk that he gave some years earlier in 1959 with the title There's Plenty of Room at the Bottom, which foresaw the development of nanotechnology. I teach a freshman seminar at Caltech, and the first paper we read in that class is this one, because I want to get the students in the mood to think about the future of science and technology, not from the perspective of what's feasible now, but rather what the laws of physics will allow us to do. And that was the attitude that Feynman took in this talk. He suggested, for example, that it ought to be possible to perform computations with computer elements that are far, far smaller than what was known in 1959. He suggested that computers, as they grow more complex, would have emergent properties, including intelligence. And he also talked about manipulating individual atoms for purposes of engineering. And that was not something that people had much discussed at the time. In fact, the pioneers of quantum mechanics, like Schrodinger, ridiculed the idea that you could do a measurement on a single atom. They thought of measurements as something that you perform on an ensemble of many atoms, not an individual atom. But now we routinely manipulate the state of a single atom. And Feynman foresaw that there's no reason why that shouldn't be possible. So this was a really revolutionary and brilliant idea. How did the world respond? Well, not very much at all for a while. There was an important step a few years later when David Deutsch tried to formalize Feynman's idea of a quantum computer and describe it mathematically. That was a useful step, and it helped to put quantum mechanics in the language that computer scientists could appreciate. And one computer scientist in particular who was inspired by Feynman's talk was Umesh Vazirani. He went further than Deutsch in formulating the idea of a quantum Turing machine and some of its properties in 1993. And for Vazirani, the motivation for doing so, above all, was to try to capture the essence of how quantum physics is different from classical physics in the form of a computational model. Well, what made interest in quantum computing really take off in 1994 was Peter Shor's discovery of quantum algorithms that theoretically would make it possible for a quantum computer to efficiently solve the problem of finding factors of large numbers and computing discrete logarithms. That generated a lot of excitement. It brought people into the field, including me. Now, at the time, I didn't know much about computer science or algorithms, but I was really struck by the idea that the problems that are easy or hard, the problems that we can solve with advanced technologies versus the problems that are just forever out of reach, that distinction depends on this being a quantum world instead of a classical world. I thought that was one of the most interesting ideas I'd ever heard. And thinking about it eventually led me to change the direction of my own research from elementary particle physics and early universe cosmology to quantum information. Now, there's an interesting connection between Shor and Vazirani. The way Shor's interest in quantum computing arose as he heard Vazirani speak about it in 1992. And as Shor described it in a recent memoir, I probably understood it better than other computer scientists because of the amount of physics I'd taken in college. Aha, Peter Shor was a Caltech undergraduate, and we crammed quantum mechanics down his throat, even though he was a mathematics concentrator. And he realized first that it would be possible to efficiently compute discrete logarithms using a quantum computer, and spoke about that in an informal seminar at Bell Labs. And the rumor about that talk spread across the country, eventually reaching Vazirani. Vazirani made contact with Shor, who was in bed with a cold at the time, telling him, I hear you can factor efficiently with a quantum computer. What was odd about that is that Shor hadn't mentioned the application to factoring in his talk at Bell Labs, but as the rumor had spread across the country, it had become garbled, and Vazirani heard it as a factoring algorithm. It so happened that by the time he made contact with Shor, Shor had realized that similar ideas allow one to solve factoring efficiently as well as discrete logarithms. As Shor puts it, after that, the news spread like wildfire. Well, yes and no. It spread, but although the archive existed in those days, Shor did not post his paper on the archive. So to hear about this development, you had to be in the circle of people who were sending Shor's paper back and forth. I was lucky enough to be in that circle, and I was very intrigued. So here we are. A lot of people came into the field of quantum computing. As you know, it continues to thrive, but it's been 31 years since Shor discovered the factoring algorithm. We're still not doing quantum computations that are cryptologically significant. So why is that? And what's taking so long? Well, quantum computing is hard to do. And what makes it hard is that we want a quantum computing system to obey a set of criteria that are almost in conflict with one another. On the one hand, we want qubits to interact strongly with one another so we can rapidly process the information that the qubits encode. But we don't want the qubits to interact with the environment, which would cause a quantum computation to fail. But we do want to be able to control the computer from the outside to make it do what we want it to do and eventually read out an answer to a computational problem. And it's very hard to build a platform that satisfies these criteria simultaneously. So it's taken decades of technical progress to get where we are today. The reason it's so important to prevent information from leaking to the environment is because of a fundamental difference between quantum and classical information, namely that we can't observe the state of a quantum system without disturbing it in some uncontrollable way. That's true of quantum information, not true of classical information. So if information leaks to the outside, even if we don't observe it ourselves, if it can in principle be observed, that's just as bad. It causes the phenomenon we call decoherence, and the quantum computer starts to behave like a classical one. So if we're going to do a quantum computation reliably, we have to keep the information that's being processed during the computation almost perfectly isolated from the environment. And that's extremely hard to do. And that was appreciated right from the start. Within just weeks after Shor's paper started to circulate, a very good physicist, Bill Unruh, did computations pointing out that a quantum computation wouldn't remain coherent long enough for it to outperform what we can do with conventional computers because of the decoherence phenomenon. Another skeptic was another hero of the physics of computation, Rolf Landauer. And for Landauer, what he found most concerning was not decoherence, but the problem of precise control of the quantum computer, since the quantum state is a state vector which lives in a continuum. Small errors in a computation could build up over time and eventually cause the computation to go off track. Both of these problems were solved by the idea of quantum error correcting codes. Here again, Peter Shor had an outsized role. Aside from discovering the factoring and discrete log algorithms in 1994, by the fall of 1995, he introduced the idea of a quantum error correcting code, which could, in principle, solve both the decoherence problem and the control problem in a quantum system. But that's not enough by itself, because we also need to show that we can perform computation and error correction even if all the operations we perform with the quantum computer are subject to noise. That required the theory of fault-tolerant quantum computing, and by the spring of 1996, Shor had built such a theory and described fault-tolerant protocols that in principle could make quantum computing more accurate. Now, I'm being unfair here because, of course, there were a lot of other people thinking about these issues in that time frame, and in particular, one was Andy Steen, who independently of Shor proposed a quantum error correcting code in the fall of 1995. And by mid 1996, Steen and Calderbank and Shor had formulated a large family of quantum error correcting codes, what we now call CSS codes, in their honor. For some reason, which I can't really explain, Steen's paper was sent to me to referee So I'm breaching confidentiality by telling you the content of my report, which begins: the paper is a major contribution to quantum information theory, one of the most significant in recent years. So I'm glad I got that right. By the fall of 1996, we could see had erected a satisfying theory of fault tolerant quantum computing and had recognized the idea of an accuracy threshold that if the probability of error for each operation in a quantum computation is below a threshold value, and if the errors are not too strongly correlated, and if we can do parallel processing and dump entropy, then in principle, we can perform arbitrarily long computations on a quantum computer with arbitrarily small error and at a significant but acceptable overhead costs. So for theorists, that settled the question of whether quantum computing is possible and convinced us that it was inevitable. But understandably, there were still skeptics. One was Serge Haroche, who knows as much as anybody about decoherence, having studied it for most of his career. And he appreciated the advance of quantum error correction, but he made the reasonable point that, in a paper with Ramon, that the implementation of error correcting codes would be exceedingly difficult. And he said, in this sense, the large scale quantum machine, though it may be the computer scientist's dream, is the experimenter's nightmare. And I guess it's fair to say, in a way, that's still the case. Another important contribution in that era was from Alexei Kitaev, who brought together the theory of fault-tolerant quantum computing with the mathematical subject of topology and introduced the idea of physical fault tolerance, that it's possible in principle to build hardware that has an intrinsic resistance to decoherence and other sources of error. And he proposed quantum codes based on topological principles. And both that code construction and the idea of physical fault tolerance continues to inspire further advances. What these pioneers recognize is that if we want to protect a quantum computation from the effects of error, then we should encode the quantum information that's being processed in a very non-local manner in a highly entangled state, so that as the environment probes the system by interacting with parts of it one at a time, it can't get access to the protected information, and therefore it doesn't have to damage it in an irreversible way. And we've also understood how to efficiently process information that's encoded in that highly entangled form. Now, there are big questions which could have been asked, and to some extent were asked already in the 1980s. How are we going to scale up to quantum computing systems that can solve very hard problems? And once we do so, what will be the most important applications for science and for industry? I think we're still far from having the definitive answer to either question. Now, when it comes to applications, we're looking for problems that are quantumly easy, can be solved by quantum computers, classically hard, are beyond the reach of conventional computers, and also useful. So somebody cares about the answer that we obtain. And when it comes to scaling up, we would like the fundamental devices, the qubits themselves, to be higher quality. We envision using error correction to boost the scale of the computations that we can perform. And we have to address some very daunting issues in engineering a large system in which many qubits are well controlled. When it comes to applications, what was correctly emphasized by Feynman and Shor and many others, that there are problems which we can solve quantumly and can't solve classically in any reasonable amount of time. And so it's a compelling question. What are these problems that are both classically hard and quantumly easy? And we've learned a lot of things about that in the past 30 years. I think there's a great deal more to learn, and that as our quantum technology advances, the experimentation with the devices will accelerate the search for new applications. But really, the best answer we can currently foresee is the one that Feynman had in mind, that we expect that a quantum computer will be able to simulate efficiently any physical process that occurs in nature. Feynman and I were colleagues at Caltech, and we frequently talked about physics in the 1980s. We never talked about quantum computing per se, which I wasn't particularly interested in at the time. But we did talk about computation because we were both interested in what could be done to advance our understanding of nuclear matter, in particular, what quantum chromodynamics says about fundamental physics. We were interested in what we can learn about that using computers, a topic that was starting to get traction in the late 70s and early 80s. But Feynman appreciated that there are some problems that would be really hard to answer with computers, including ones as fundamental as what happens when we bang together two protons at very high energy? What products are produced in that kind of reaction? And I think thinking about that was part of what provided the incentive for him to propose the idea of quantum computing. And as Feynman recognizes the answer to Dirac's remark, with quantum computers, by solving the many electron problem, we should be able to go much further in studying the properties of complex molecules and exotic materials, and also study fundamental physics in new ways, for example, by simulating the quantum behavior of a black hole, or what was happening in the early universe right after the Big Bang. Now, to do all that, we need hardware. And there are a lot of different ways in which qubits can be instantiated, and many of those are being pursued and are steadily advancing. And it's important for us to continue to develop these different hardware approaches in parallel, because we don't currently know for sure which hardware is going to have the best prospects for scaling up to large systems that can solve hard problems. It could be a hybrid of different technologies, which turns out to be most helpful. Each technology may have its own niche, and there might be different approaches to quantum computing we're not even thinking about now, so the fundamental research has to go on. Some of the leading contenders I'll briefly describe. One possibility is for the qubits to be encoded in individual atoms, where the atom is either in its ground state or some long-lived excited state. If those atoms are electrically charged, if they're ions, then we can trap them with electromagnetic fields. And then, addressing the atoms individually with a stable laser, we can prepare a desired state, we can read out the state of the atom, and we can perform single qubit quantum operations. In an ion trap, as in all the modalities, the hardest thing is to perform two qubit operations. By building a circuit of many such operations, we can do universal quantum computing. And in the ion trap, that's done by taking advantage of the vibrational modes in the trap. Because those modes are shared by many ions, we can get any pair of ions to interact with one another, but the gate speed is determined by the vibrational frequencies. Typically, it takes tens of microseconds to do a single two qubit operation. For scaling up, we envision a system with many traps which can share entanglement by means of optical interconnects or by shuttling ions back and forth between traps. Another approach, which is heroically pursued by IBM and other companies and labs around the world, is superconducting circuits, where we now have systems with over 100 qubits in a two-dimensional array with nearest neighbor coupling among the qubits. The qubits are typically transmons, which you can think of as artificial atoms, but unlike the actual atoms in an ion trap, these have to be very carefully fabricated and frequently recalibrated. We can couple a transmon to a microwave resonator for the purpose of reading it out, and we can perform gates on single qubits with microwave pulses. Two-qubit gates can be performed in a variety of different ways. One is to have tunable couplings, which can turn on and off the interactions between neighboring qubits, where the typical time to do a two-qubit gate is tens of nanoseconds. For scaling up, we envision devices with probably many chips and interconnects between the chips. We'd like to reduce the number of control lines needed for the microwave signals that come into the device. We'd like better materials and fabrication, and possibly also alternative qubit designs. A third modality, which has been advancing rapidly in the last few years, is neutral atoms trapped in optical tweezers. It's possible now to have hundreds or even thousands of atoms, each one held by a single laser beam. And these atoms can be excited to highly excited states that strongly interact so that we can do fairly rapid two-qubit gates. Furthermore, the atoms are movable, the tweezers are reconfigurable, so there's no geometrical constraint on which qubit interacts with another qubit. And it's possible to perform global operations in which many gates are executed in parallel. Now, right now, the movement of the atoms is relatively slow, and so is the readout. So it's important to improve those things. And the atoms get lost, so there's a need for continuous loading of fresh atoms. And that's a technology which is also under development. So what about applications? What can we do today? It's sometimes said that we are in the era of NISQ, noisy intermediate scale quantum processing. The term NISQ doesn't have a precise quantitative meaning, but it conveys an idea that with the devices we have now, say with of order 100 qubits, we can't, by brute force, simulate with a conventional computer what the quantum computer does. But noisy reminds us that these devices today are not error corrected, and the noise is a serious limitation on their computational power. As it stands now, there is no proposed application of NISQ computing with commercial value for which a quantum advantage has been demonstrated if we compare to the best classical hardware running the best algorithms for solving the same problems. NISQ is valuable for scientific exploration, but not necessarily currently valuable as a commercial enterprise. And we don't have persuasive theoretical arguments indicating that commercially viable applications are going to be found that don't use quantum error correcting codes and fault tolerant quantum computing. What we'd like to have is FASC technology, fault tolerant application scale quantum computers that can run a wide variety of useful computations, but by some estimates, such a device would have to be able to perform of order 1 trillion operations in a quantum computation, which would mean that the error rate per gate would have to be about 10 to the minus 12. And that's vastly better than what we have today, where under the best conditions, the probability of an error every time we perform a two-qubit gate is about 1 in 1,000. So we have a chasm of 9 orders of magnitude we have to cross. It's not plausible that that can be done anytime soon without using quantum error correction. In fact, we'll probably need devices with millions of physical qubits to run applications at that scale. So when are we going to have that? Nobody really knows. It might take a few decades. It might happen faster if we make appropriate investments and direct our efforts strategically. Now, the applications that Feynman had in mind are still top of mind. Remember, Dirac said that the equations are too complicated to be soluble when talking about the many electron problem. That's a little misleading because we have many heuristic classical algorithms that are often very successful in practically relevant settings. And the algorithms for simulating many particle quantum systems using classical computers have been improving rapidly in the last few years, just through better algorithmic insights. With quantum computing, we're going to be targeting what is now a relatively small, strongly correlated corner of chemistry and material science, where the systems are highly entangled and all of those classical methods falter. And that makes it hard to estimate how useful quantum computers are going to be in physically relevant situations that are beyond the reach of classical methods, because we don't know how rich the world of highly entangled many electron systems will turn out to be. Meanwhile, for understandable reasons, there's a surge of interest in using artificial intelligence to solve many particle quantum problems, and that is promising. But for now, AI applied to quantum systems suffers from a dearth of training data in the strongly correlated regime. We can anticipate that eventually quantum computers will be able to accelerate progress by providing training data that can be leveraged by AI in classical computers to make predictions about more complex systems, molecules, and materials. Now, what's particularly promising, at least from a scientific point of view, is using quantum computers to simulate how highly entangled systems evolve with time, because that's quite hard to do with classical computers. But we have to ask the right questions in order to get scientifically useful answers. In some cases, quantum systems are localized, meaning that as they evolve, they don't become very highly entangled, and so they might not be so hard to capture with classical computations. In other cases, the systems are strongly chaotic and quantum information becomes scrambled very rapidly. That's hard to simulate accurately with a classical computer, but it won't necessarily be so interesting if the system very rapidly converges to thermal equilibrium, and the process of reaching thermal equilibrium might not be so scientifically informative. Well, we just have to ask the right questions. I think there are many ways in which scientifically informative surprises can be expected as we simulate dynamics far from equilibrium. One thing I've been interested in is what Feynman was interested in the 1980s, simulating collisions of fundamental particles at high energy using a quantum computer. Eventually, we're going to do things like that, which we just can't do with conventional computers. And we're already seeing some of those scientifically informative surprises today. Now, all this is contingent on being able to overcome limitations from the noise in quantum devices. There are two different approaches to that. One is called quantum error mitigation, and essentially what it means is that we characterize the noise in our device well enough so that after doing a quantum computation and running it many times, we can post-process the results to minimize the effect of the noise on the answers that we obtain. And that's used now. In fact, it's essential for getting usable answers from the quantum processors we have now. However, it does not scale well. The number of times we need to run our quantum computation as the system size increases, that number of run times goes exponential with the size of the system that we want to study. Quantum error correction solves that problem in principle. It has a much more reasonable asymptotic overhead cost as the size of the input to our computation increases. But we can't really use it in computations we care about today. What do we need to use quantum error correction? Well, we're probably going to need better 2-qubit gate accuracy than we have now, and also a lot more physical qubits and the ability to control a very complex system involving many qubits. To give you an idea what we're up against, come back to Kitaev's proposal of what we call the surface code, which in some ways is the most promising approach to doing fault-tolerant quantum computing in the relatively near term. We like the surface code because controlling the errors requires only local processing, geometrically local processing in a two-dimensional layout. And this is a code that can tolerate a pretty high physical error rate. There's a threshold for the surface code of accuracy of about 1%. Once the error rate per 2-qubit gate is below that threshold, then as the code grows in size, the logical error rate, the error rate for the protected information, goes down exponentially. The quantity d here, called the distance of the code, scales like the square root of the number of physical qubits in the code block. So let's say that we had a physical error rate of 1 part in 1,000. That's a little better than we currently have in multi-qubit devices. Let's say we want a logical error rate of about 1 in 100 billion. Then we would have to have a code with hundreds of physical qubits protecting each logical qubit, and then a comparable number of qubits, which are ancillas for reading out error syndromes. And so we're up to nearly 1,000 physical qubits with that will protect just a single logical qubit. We're going to need a lot of physical qubits. So what's the current state of the art? That's captured by recent results from the Google quantum AI team with their 105 qubit processor called Willow. They've been able to perform hundreds of consecutive rounds of syndrome measurement in that surface code, where each round lasts for about a microsecond. And most significantly, they showed that as the code increases in size, as its distance increases from 3 to 5 and from 5 to 7, each time the error rate declines by a factor they call lambda of about 2, indicating that as the code increases in size, we should be able to suppress the errors further. Also significantly, they were able to decode the error syndromes and, in effect, correct the errors in real time during the computation. That's important because in a quantum computation, we will need to frequently read out logical qubits and then perform subsequent operations conditioned on those measurement outcomes. So if it takes too long to decode the logical information, that will slow down the logical clock speed. So as we look ahead, we'd like to have larger values of lambda, larger codes, and the next big milestone will be performing 2-qubit gates on logical qubits with error rates per gate much better than we can achieve with physical qubits. Now, there's also error correction progress being made with other platforms besides superconducting circuits, in particular the atomic platforms, both Rydberg atoms and ion traps. So, for example, the Harvard MIT Quera group has run computations with 48 protected logical qubits on a 280 qubit device using neutral atoms and optical tweezers. However, in these atomic platforms so far, it's only been possible to perform a few rounds of syndrome measurement as compared to millions of rounds in the Google demonstration. And these demonstrations on atomic qubits make use of post-selection. That means when errors are detected, the circuit run is discarded. That's a scheme that doesn't scale up to large codes and large computations. Now, there's a lot for theorists to do. We love the surface code because it only requires local connectivity in 2 dimensions, and it can tolerate pretty high errors, but it does have a high overhead cost. Fortunately, there are codes which are recently discovered which are much more efficient in the number of protected logical qubits per physical qubit, including beautiful work done by the IBM group. The catch is that for these more efficient codes, we need processing which is geometrically non-local. Now, that's pretty well suited to the atomic platforms, in particular the tweezer platforms, where the qubits can be reconfigured and we're not so limited by geometry. We really need some fresh thinking about how to scale up to a large system, about the type of architecture which will make the control requirements for running a large quantum computer acceptable. And I think we really should be rethinking the general principles of fault tolerant quantum computation. We may be missing some very good ideas by thinking about how to protect quantum computers from error by following too closely the ideas that originally arose in classical computing. A reasonable goal for the relatively short term is a megaquart machine, one that can perform about 1 million 2-qubit quantum operations. That would mean we would have to have a logical error rate of about 1 in a million, maybe not quite as small as that, because we can make use of error mitigation methods at the logical level, and we'll certainly do that. But the error rate will be low enough so it's not something we expect to be able to achieve without using quantum error correction. And importantly, we think there are interesting things that can be done with a megaquart quantum machine, which surpass what we can do with classical computers or with NISQ computation or analog quantum simulators. For example, by running a circuit with about 100 logical qubits with a circuit depth, a number of time steps of about 10,000. So what will it take to realize a megaquart machine? That actually depends on a lot of things. But a reasonable estimate is that it could be done with a few tens of thousands of sufficiently high quality physical qubits. So when are we going to have that? I don't know. If it happens in the next few years, I think the most likely modality will be Rydberg atoms with tweezers, which seem to have the best near-term prospects for scaling up. What will we do with such a machine? Well, I don't know what will be the best thing to do, but as a scientist, I'd be particularly interested in simulating highly entangled quantum dynamics in that megaquark regime. Will it have commercially valuable applications? Well, I can't promise you that. We're in an era of co-design where it's essential to get good performance out of our hardware to adapt the error correction scheme and the applications that we run to the strengths of the hardware. And conversely, we get guidance in developing the hardware from our ideas about the error correction protocols we'll use and the applications that we want to run. Well, coming back to Feynman, I have a view of quantum information science, which I think he would have resonated with, which is that we're in the early stages of the exploration of a new frontier of the physical sciences, what we could call the complexity frontier or entanglement frontier. It's different than the short distance frontier of particle physics or the long distance frontier of cosmology, areas I've worked on earlier in my career. But like those, it's very fundamental and exciting. We're acquiring the tools to build and precisely control very complex states of matter, highly entangled states of many particles, which we can't simulate with our most powerful supercomputers, and for which we don't have the theoretical tools to understand very well how they behave. And that opens opportunities for scientific discovery. In addition, we do anticipate sizable economic impact from quantum computing down the road. But we'll do the science first. And eventually, that science will be turned into economic value. What can we expect in the next couple of years? Well, I think we will see encouraging progress towards scalable fault-tolerant quantum computing. I think the pace at which we get scientific insights from either circuit-based quantum computing or programmable quantum simulators will increase in the next few years. And our ability to control many entangled particles also has implications for quantum measurement. In particular, we can anticipate by controlling complex states of matter, improvements in optical atomic clocks. If we try to envision the longer term history of quantum mechanics, 100 years since it was discovered, we're hampered by our limited imaginations. But we might characterize the difference between the past and the future this way. Over the last 100 years, we've been very successful at understanding the behavior of many weakly correlated particles, electrons, photons, atoms, molecules, and the insights that we've gained into, for example, the propagation of electrons in semiconductors, or the condensates that can occur for many photons or many atoms, have had inestimable scientific and economic impact. The big challenge and opportunity for the next 100 years is to arrive at comparable insights into the behavior of complex, highly entangled matter, highly entangled states of many particles, and to make use of those insights for the benefit of humanity. This entanglement frontier is vast, it's inviting, and it's largely unexplored. I think we can anticipate that the surprises that await us as we explore the entanglement frontier in the next 100 years will surpass the discoveries of the first 100 years of quantum mechanics. So we should give thanks to the quantum pioneers of the past and the quantum heroes of today. But especially, I want to wish good fortune to you, the quantum explorers of the future. Thanks for listening. And I don't know if, I hope you've been able to hear me. Somebody tell me in the chat that you could hear me, and I'll feel better.
You can't hear me, right, John?
All right. That's good to know. Now, I don't know, for the questions, unless we can fix the audio so I can hear you, how is it supposed to work? Are you going to give me written questions? I think somebody is supposed to be moderating this. Second stop. Okay.
If everyone can maybe just hold up in the chat for just a minute so we can communicate with John, that would be helpful. I know everyone is just saying thank you, but just hold on 1 second so we can message him.
No, I can't hear Olivia. Someone says that she's talking. So what am I doing wrong here? Try a different speaker. Well, you know what? I'm gonna try disconnecting and reconnecting. See if that helps. Glad you're able to hear me. Talk to me, Liv.
John, can you hear me?
Yes, I can.
Yay! Okay, great. Well, rest assured, I could hear your lecture loud and clear. It was fantastic. Everyone in the chat was just basically chiming in saying it was great.
That's good.
And we didn't have any audio issues or anything. And so I guess just disconnecting it fixed the audio problem in the end. So let's get to some questions now. Okay. So this is a really interesting one. As an industry research professional, many of us are trying to stay on top of quantum computing research. However, many industries are interested in quantum computing, but it is not yet useful or profitable to us, so our bosses aren't willing to invest too much of their money and time in quantum. Yet new research is rapidly being released. So, how can research professionals, not necessarily in quantum, but professionals, stay up to date with new algorithms and updates in industry?
Well, there's an amazing amount of stuff online. Um,
There is.
of course, what I would tell a student, a graduate student at Caltech, is to regularly follow the archive and try to stay on top of interesting papers. That's not a very good suggestion for the type of person you're describing, but there are many conferences um, where accessible talks are given. One that I think is particularly valuable for a spectrum of researchers, from real experts to people who are less familiar, is the Simons Institute has a quantum colloquium where they regularly have speakers talking about recent developments, followed by panel discussions, which are often very informative, where the speaker and a few other experts kick things around, typically moderated by Umesh Vasarani, who, as you may have noted, was one of the characters in my spiel. So that's one resource that I especially recommend.
Great. This one I think might be up your alley. How are quantum computers being used or are going to be used in the field of particle physics?
Well, I think we have to take a long-term view here. Um, there are several possible answers to that question, but the one that interests me the most is the one that I mentioned in passing during my talk, uh, which is there are questions about dynamics in quantum field theory and even in quantum gravity, which I think is especially exciting, that are too hard to solve with conventional computers. Now, we tried to do some estimates of the resources you would need to really simulate quantum chromodynamics, for example, a collision of particles, and that's not going to happen for a long time because that's going to have to be fault tolerant, and it's probably going to require a lot of logical qubits as well. That doesn't mean it's not important and interesting to be thinking about that now. I like to think about the development of what people call lattice gauge theory in particle physics. The idea, and I discussed this with Feynman multiple times, of using conventional computers to study some properties of hadronic matter um, started to be discussed in the late 70s, early 80s. And actually, Feynman pointed this out. He said it's going to be decades before we'll have the computational power for that to be quantitatively informative about quantum chromodynamics. But there were people who saw the potential and actually developed the hardware. Some of the progress that occurred in the 1980s in parallel computing was driven by the desire to simulate quantum chromodynamics at larger scales. And it took 20 plus years before that really became a useful part of the particle physics program, but now it is. And there are a lot of things that we can compute using lattice QCD, lattice quantum chromodynamics, that are relevant to current searches for dark matter and neutrino physics and things like that. Like I said, some things in quantum field theory are just too hard to compute with conventional computers. That's where quantum computers will come in. And, it's going to be most likely decades, as it was in the case of lattice gauge theory, for that to really become quantitatively informative. But in the meantime, I think we're not so far away from being able to do simulations of quantum field theory with quantum computers that surpass what we can do with classical computers. I'm particularly interested in studying quantum field theory in two spatial dimensions, simulating dynamics, because that's really hard to do classically. And I think with the mega quap machine I referred to probably isn't quite powerful enough to do that in a useful way. But I don't think we have to go so far beyond that to get informative results. So, that's something to think about on a 10-year time scale. Simulating QCD, maybe that's a 30-year time scale, but you guys are all young, so you've got time. And of course, there are other applications that are, well, potentially could be impactful having to do with dealing with big data.
Right. And there's been a couple interesting papers in the particle physics quantum computing overlap field recently that I've checked out. And I'm not a particle physicist, but I found them to be very interesting. So maybe we can put some of those in the chat as well. Okay. This is another interesting one. So you have been a promoter and a scientific communicator in quantum information for some time now.
So have you.
That's true, but I think you might have me beat by a little bit. What has been the biggest challenge in promoting quantum computing in the community that you have seen, that you have worked to resolve?
Well, if we go back to when I first got interested in quantum computing, um, my friends who were particle theorists like I was just didn't get why I thought this was so interesting.
Okay, that's really
And
interesting.
and in particular, I was intrigued in the 1990s already by quantum error correction,
Mhm.
not just as something that would that engineers need to know about, but as something providing fundamental insight into quantum physics. It's an amazing thing, and I think maybe young people sort of take it for granted, whereas it's kind of a miracle, right? Quantum systems, uh, back when I was a kid, were single atoms or something like that. The idea that you can make a quantum system macroscopic and have precise control over it, despite decoherence, despite the fact that the control at the physical level is imperfect, is an amazing thing. And in fact, error correction has given rise to insights that have nothing to do with engineering big systems, but understanding matter, understanding the types of phases of quantum matter we can get. And they've even given us, I think, some insight into how quantum space-time works, because that's also a kind of quantum error correcting code. So anyway, in the early days, it was challenging to try to convey why it was so exciting. I think the problem I have now is I'm striking the right balance between optimism and pessimism, because I feel an obligation to push back a little against expectations that I think are unrealistic,
Mhm.
not about the long-term impact on which I'm very bullish, but the time scale for significant economic impact. Nobody really knows. But I think if people are expecting uh, quantum computing to have broad impact on society in 5 years, they're going to be disappointed. Um, but it's still enormously exciting scientifically, and in the long run, it is going to have a big impact on society. So so I push back. I say, well, hold on, let's not get ahead of ourselves. It's going to take a while. It's a long term enterprise, and we really need the fundamental research. I think part of the reason for pushing back is the attitude you sometimes hear is, okay, we've done the science, now it's engineering. I don't agree with that at all. I think we're going to need a lot of fundamental research to get where we want to go with quantum computing. And what we're doing now is all based on fundamental research that occurred in the past few decades. At universities, we should continue to think longer term into the future than industry typically does, and
Mhm.
conceive things that industry will be doing in 20 years. So I want to convey the promise, the excitement, but also sometimes, I'm the skunk at the party saying, you know, let's be realistic.
Well, sometimes we're all the skunk at the party.
Mm-hmm.
I think I would have said, something very similar too. It can be hard to balance between what I think a lot of people call hype, between being genuinely excited and optimistic about things that you believe are going to happen. Um, it's very interesting, though, that your colleagues at the beginning of your career didn't see, well, I'm biased, but they didn't see the excitement in this.
There were a few who did, but it took, and eventually it happened. You see, actually, when it happened fast,
Okay.
right? In the 1990s, people who were interested in particle physics, I couldn't convince them quantum error correction was interesting.
Hmm.
But about 10 years ago, maybe a little longer, um, in particular, from thinking about quantum space-time and recognizing the role of quantum error correction, basically space-time, most people in particle, well, I don't know, I shouldn't talk about what most people think. Many people think that space-time itself is not fundamental. It's an emergent property. And the key thing that kind of holds space-time together is quantum entanglement. And the way to characterize that and describe it really is in the language of quantum error correcting codes, uh,
Mm.
which is a very powerful language. And now people who work on quantum gravity, many of them, feel they've got to know that stuff. And they do. They know about quantum error correction. They know about, I get that to stop. They know about quantum complexity, and they see it as a vital part of the subject. It takes time.
Sure. That's really interesting, and that I think answers one of the questions I was going to ask actually, which was somebody asking if the language of quantum error correction and also entanglement can be applied in other areas that you wouldn't maybe necessarily think. Um, I'll ask a few more. You've already been super generous with your time, but maybe this one always comes up, and you probably always get this. But what are the biggest challenges or hurdles that must be solved before quantum computers are at the fault tolerant level and we are providing practical solutions to large scale applications?
Well, there are a lot of challenges.
Indeed.
um, I'm not sure how to answer that, but there are a lot of things we have to do. Um, and to some degree, the answers are platform specific, and uh, in other senses, they're more general. But really, look at what we're trying to do. It's an incredible challenge, right? We've got systems that are pretty cool, with a few hundred qubits now. Um, and we're envisioning, in order to run algorithms on fault tolerant quantum computers, systems with millions of physical qubits. Um, and there's an engineering side to that, which is very daunting, but I think there's also a fundamental side. I don't think we, I think we can come up with much better ideas about how to conceive and design a quantum computing architecture than we have so far, which will, uh, you know, reduce the requirements in terms of physical qubits, in terms of power, and improve reliability and stuff like that. So I think for a theorist, that's a great thing to be thinking about. in more concretely, again, if you're a theorist, it's very exciting now what's been happening in quantum error correction. New codes being discovered, new protocols for doing processing with these codes, but there's a lot of room for improvement there. In particular, if we're going to make use of these codes that have higher encoding rate but are require geometric non-locality. If you're somebody at IBM or thinking about solid state um, instantiations of quantum computing, then you have to be thinking about to what extent can we um, build a system that has the long range connectivity that will want to take advantage of those codes. We really need new ideas about applications too. My feeling is that we probably just scratched the surface, and there are many applications of quantum computing we just haven't been smart enough to think about. And but that's one area in which fundamental research can make a huge difference, coming up with new ideas for applications. You still there, Liv? Maybe maybe she had the same problem I did. I don't know. So I can see the chat here. Are you people still out there? Somebody
John, can you hear me?
I hear you, yes.
Great. Okay, it's Marina.
Oh,
I
yeah.
think Olivia might be having some technical difficulties, so I'm going to put her in the way.
Boy, I know what that's like.
I know. Crowdcast is not our friend today, but everyone, thank you for bearing with us. And John, thank you for for also bearing with us. I think if you go, do you see your sidebar where there's the
Yeah.
chat? There's a couple of other things. There's a Q&A. There's a little box second from the top with a question mark in it. And that's the Q&A panel. So if you click on that, you can choose some of the questions that you'd like to answer. The folks in the audience have upvoted a few of them.
Oh, yeah, I see.
Yeah.
Oh, okay. So I'm seeing at the top of the list.
Mm-hmm.
Oh, this one's about interpretations of quantum mechanics. Uh-oh. So the question is, in my understanding, most of the quantum computing framework is now based on the Copenhagen interpretation. How different interpretations of quantum mechanics can change or affect the structures of the existing algorithms. I don't quite accept the premise. Well, look, there are a lot of deep questions about the foundations of quantum mechanics and good questions to think about. They interest me, generally speaking, only to the extent that they lead to experimental tests we can do to distinguish these different interpretations. I don't think you have to believe in the Copenhagen interpretation, and by that I mean the idea that measurement is a fundamentally different physical process than unitary evolution. I don't know if that's what you mean by the Copenhagen interpretation. You don't have to think that's true to draw the same conclusions about quantum computing that somebody would who believes in the Everett interpretation and that everything is unitary. But interpretations can still be important because they provide us with some intellectual guidance. I think it's interesting, for example, although I don't agree with some of the things he said about this, that David Deutsch, who's a fervent believer in the Everett interpretation of quantum mechanics, envision the power of quantum computing in that language, and that guided him to make proposals and conjectures about the power of quantum computing, which turned out to be valuable. So different interpretations are useful if they actually can be distinguished by some kind of experimental criterion, or if they give us new ideas. And that's true in quantum computing just as it is in other areas of quantum mechanics.
All right. Sorry, guys. I disappeared for a second. But I'm back. We're 20 minutes past the hour, I think we should thank John so much for being so generous with your time. And thank you again for the wonderful lecture. We got so many great comments in the chat. I hope you at least got to see a few of them. People were very active. And I also want to thank the audience for your participation as well. So again, thank you, John, so much for participating in our 5th edition of this summer school. It's been wonderful to have you, and just thank you again.
And thank everyone for listening and for all the great questions.